Hello and welcome to this FP3 exam paper walkthrough. This was the January 2024 paper. You were allowed an hour and a half, the formula booklet and a calculator. Question number 1. Show that this integration is equal to p pi, where p is a rational number to be determined. Jumping straight in. Integral 4 root 3 8 over 16 plus x squared dx. I am immediately going to turn to the formula booklet. This is the FP3 section of the formula booklet. The integration bit, you can see we can compare what we've got on the left with this fraction here, where a would be a 4. So 1 over a arctan x over a. So we've got 1 over a squared plus x squared would give us 1 over a arctan x over a, like this. So if I pull out the 8, 4 to 4 root 3, 1 over 4 squared plus x squared dx is going to give us 8 times 1 over 4 arctan of x over 4 from 4 to 4 root 3. So that is 2 times arctan of 4 root 3 over 4 is arctan of root 3, and calculator tells me that's pi by 3, minus arctan of 4 over 4 is a 1, that's pi by 4, which is pi by 12, and gives us an answer of pi by 6. P therefore is equal to 1/6. Was it a rational number? Yes, a rational number. Now we need to determine the exact value of k, for which this integral gives us pi by 12. So if I copy that down here, then I'm going to integrate as normal, put in the limits, and then make it equal to pi by 12. Back to the formula booklet, and this time we can see it is this one. We can manipulate it to make it look kind of like this, and that will be arc sine x over a. So if we can get something that looks like a squared minus x squared rather than 4x squared, then that will give us arc sine x over a. To do that, well, we can bring the 2 outside, and then in here we want to factor out a 4 to make that 4 lots of 9 over 4 minus x squared, like that, and we can square root that 4, and that will cancel with the 2 on the outside, and that will equal just 1 over 9 over 4 minus x squared. It's a slightly awkward a, but that will work. That gives us a is equal to 3 over 2, and so this integral is equal to arc sine x over 3 over 2, and that has the limits from 3 over 4 to k, and all of that has to equal pi by 12. So we've put those limits in now, and basically we're just solving the equation. Arc sine 2k over 3 minus arc sine a half, which is pi by 6, and that has to equal pi by 12, and this is still arc sine 2k over 3, pi by 6 plus pi by 12 is a pi by 4, so then we can bring that on the other side. Sine of pi by 4 gives us 2k over 3, that's a root 2 over 2, so a little bit of rearranging here, and we get 3 root 2 over 4. Is k supposed to be irrational? The exact value, yep, that makes it sound like it's okay. K is 3 root 2 over 4. That finishes our first question. On to question number 2. So we've got 2 matrices given to us, T and U. There are some missing elements, A, B, and C. Given that TU equals I, the identity matrix, determine the value of A, B, and C. So that statement is telling us that T, which has to go on the left, which is this, multiplied by U on the right. Remember, the order is very important for matrix multiplication, is equal to the identity matrix, which has 1s on the leading diagonal and 0s everywhere else. How is that going to help us? Well, I can see that if we do the third row and the first column, we're going to have A's and B's, and if we do the third row and then the third column, we're going to have A's and B's as well, which will give us a pair of simultaneous equations. So I'm doing A times 6 plus 4 times 15 plus B times minus 8, and that must equal third row first column element in the identity matrix, which is a 0. Then A times minus 4 plus 4 times minus 9 plus B times 5, and that must equal the third row third column element in the identity matrix, which is a 1. Using these two, we can find A and B. I'm going to times the top one by 2, the bottom one by 3, plus 15b is 111, and then add them together, and we get minus b equals minus 9, so b is 9. Putting that back into my first equation, 6a plus 60 minus 8 times 9, that gives me 6a is equal to 12, a is equal to 2. Now to get c, we can do the third row second column. So we've got a times minus 1 plus 4 times c plus b times a, and that has to equal 0, because that's the third row second column element in the identity matrix. But we know a and b, that's minus 2 plus 18, and if we take that over, that gives us minus 16 for c, so c is equal to minus 4. And then we have our 3 answers for A, B, and C. Part B, there's a bit more information. The transformation represented by the matrix T transforms the line L1 to the line L2. Given that L2 has the equation this, determine a Cartesian equation for L1. So we want to work backwards here. So we're saying T acting on L1 equals L2, but we know L2, not L1. So to find L1, we want the inverse matrix of T acting on L2. So I need a general point out of this rather than a Cartesian equation. So we've got 3 minus 4 and 1 from these numbers here. And that's my direction vector. And then the numbers here give me the point that I need. So that's a 1. Here that would be minus 0. And in the form z minus c, that's a minus 2. So L2 has this equation, which I can write as a general point 1 plus 3s minus 4s and minus 2 plus s. So that's this vector here, but I also need the inverse matrix of T, which is a lot of work. Oh no, okay, yes. I was going to say it's a lot of work because finding the inverse matrix for 4 marks seems strange when we still have to apply that, but because of this fact here, that tells us that the inverse matrix is equal to U. U is the inverse of T, because to get the identity matrix, you know that this is true, therefore U and the inverse of T must be the same thing. So what I'm actually going to do is U times L2. So I'll take this information down with me, and I will note also that we need a Cartesian equation for L1, so we need to put it back into Cartesian form at the end. But here's a copy of what we just had on the screen at the top there. So we're applying Oh, now I need matrix U. Can't deny that there are certainly times when this is easier on paper. So that's U, and then the line L2, 1 plus 3s minus 4s and s minus 2, and that is going to give us L1. Now we just have to apply our matrix multiplication, and that will equal 6 plus 6 times 3s minus 1 times minus 4s and minus 4 times s and minus 2. Then 15 times 1 plus 3s and c, oh, I should put c and a in, shouldn't I? C was a minus 4 and a was a 2. So minus 4 times minus 4s plus 16s and minus 9s plus 18. Third row, minus 8 minus 24s minus 8s plus 5s minus 10. That gives us 18s plus 14 here, 52s plus 33 minus 27s minus 18. So that's our general point, so we can write that as 1433 minus 18 plus 1852 minus 27s, but we wanted it in Cartesian form, so that's x minus 14 over 18 is equal to y minus 33 over 52 is equal to z plus 18 over minus 27. Just a reminder of where that comes from if you're not sure why I've converted between the forms like that. If you read off each component here, you've got 14 plus 18s equals x, and you just rearrange that to make s equals x minus 14 over 18, and then you do that for each of the three components and you get s equals in each case, and because they all equal s, then they all have to equal one another, which is why the numerator is the negative version of the 1433 minus 18, but the denominator is the positive version of the direction vector. Although the numbers look a little bit strange, a little bit larger than I would have expected, that should be correct. For part B, was there anything else? No. Moving on to question number 3. Oh, that's a lot of reading to do here. The ellipse E has this equation that tells us that A is equal to 7, where B is a constant between 0 and 7. The eccentricity is just given as E. Write down in terms of E only the coordinates of the foci and the equations of the directrices. Now that's actually quite easy because given in the formula booklet are the coordinates of the foci of an ellipse, and that's A, E, 0. The equation of the directrices are also in the formula booklet, and that's x is equal to plus or minus A over E. And we know from the equation that A is 7, which is why they've used this phrase write down rather than calculate or work out. So we've got 7e and 7 over e. S is often used for the focus. That's 7e 0 and S1, S2, the other focus, minus 7e 0. Annoying blue line there for some reason. The directrices, x is equal to plus or minus 7 over e. That's I, and that's part A finished. Part B, given these 4 bullet points, determine an expression for ps squared and pm squared in terms of ex and y. Okay, so let's just quickly refresh. There's our ellipse, the focus here, and there's a focus here. The directrix is over here somewhere, and over here somewhere. So this is AE, which we know is 7E, and this is 7 over E, and we've got a point P somewhere on E, where x is greater than 0, so on the right hand side, so let me put it here somewhere. The point S is the focus of E on the positive, so that's this one I've labelled 7E. The line L is the directrix which crosses the positive, so that's this one that I've drawn on. And the point M lies on L, such that the line through PM is parallel to the x-axis. So there's M. PS is this line here then, and PM is the one drawn dashed. P, of course, has coordinates x, y, so this distance here is y. This distance here is not x, because this is x all the way from there, so this little distance is x minus 7e, just because I've drawn the p to the right of s. This distance here is 7 over e minus x. So pm squared is very easy. We can just square 7 over e minus x, and that gives us pm squared. So I'll take this diagram, bring it down here as part B. So pm was very easy. That's just 7 over e minus x. So pm squared is just squaring that expression. 49 over e squared minus 14x over e plus x squared. Now PS we can do because there's a little right angle triangle in here. So PS squared is the hypotenuse, that's y squared plus this expression here, x minus 7e all squared, okay, plus x squared minus 14 lots of ex plus 49 lots of e squared. And because we're squaring that, it doesn't matter if you've done what I've done and put the p on the right of s, or if you put it on the other side. If you put it over here, say, then the distance here that you would use in your triangle would be 7e minus x, but squaring that would give you the same expression here. So that's ps squared in terms of x, y, and e, pm squared in terms of x and e, as required here. And then for this part C, hence, means use what you've just done here, show that this is true. To do this, you need to be able to relate these two things, remembering the equation E is equal to PS over PM. And obviously if you square all of those, that's still true. So for part C, we're using what we've just done. E is equal to PS over PM gives us PS squared equals E squared PM squared, and we can use the expressions above. Y squared plus x squared minus 14ex plus 49e squared is equal to e squared times 49 over e squared minus 14x over e plus x squared. That gives us 49 minus 14ex, which is great, that needs to cancel. With that, and then plus e squared x squared. So I'm going to bring the x's together on the left here. Still have a y squared there, and then the 49 with the 49e squared. And then we've got x squared 1 minus e squared factorized there, and 49 1 minus e squared factorized here. Now what we're trying to do is basically get to this equation here, so that we can see in the denominator this expression, and obviously in the equation we can see in the denominator b squared, and therefore we can say, hey, b squared must be equal to this expression. So we just need to divide everything by the right hand side in order to get our usual 1 on the right hand side of our ellipse equation here, and everything else should fall into place. So we've got y squared over 49 1 minus e squared, and of course when we divide through here, that bracket on top cancels, to give us the equation that we had. And we know that that means b squared equals 49, 1 minus e squared. So this was a key part of that process. Part D, given that e crosses the y-axis at the points with coordinates 0, minus 4 root 3 and 0, plus 4 root 3, that's these 2 points, determine the value of e. Okay, that's effectively saying when x is equal to 0, y is equal to plus or minus 4 root 3. And we can just put that into the equation here that we had, part D. So if I put that in, we get 0 squared over 49 plus 4 root 3 squared, which is 48 over 49, 1 minus e squared has to equal 1. That's obviously gone. So we get 48 over 49 is equal to 1 minus e squared. So e squared is equal to 1 minus 48 over 49, which is 1/49. So e is equal to 1 over 7. That's part D. Given that the x-coordinate of P is 7 over 2, determine the area of the triangle O, the middle here, OPM. A slightly awkward triangle here. So we need the base, kind of the base, which is PM. So if we have this drawn here for a second, PM is kind of like our base, and that's 7 over e minus x, and then our perpendicular height here is just the y-coordinate of P. If I bring that down, this is OPM. We know x is 7 over 2, e is 1 over 7, PM, the distance there, 7 over e minus x, 7 over 1 over 7, 49, minus 7 over 2, 91 over 2, and then we need the y-coordinate, so I'm plugging it back into this equation at the top of the screen there. So that was x squared over 49 plus y squared over 49, 1 minus 1 over 49. So that's all 48. And x is 7 over 2, so we put that in. 49 over 4. Like so, is 3/4, and that gives us a 36. Y is positive, so it's a 6. Therefore our area is equal to 91 over 2 times 6 over 2, 273 over 2. That felt like quite a long ellipse question, but I think we're finished. Yes. On to question number 4. More matrices. Given that 1 minus 2, 1 is an eigenvector of M, determine its corresponding eigenvalue. This is fairly straightforward. We just need to apply the matrix M onto that vector and see what we get. And that will be a factor of lambda different, and whatever that factor is our eigenvalue. Matrix multiplication, here we go. We've got a 0 times the 1 plus 2 plus 3. So that's a 5, which tells us straight away that the eigenvalue is 5, because that's 5 bigger than this, but to ensure that I haven't made a mistake, I'm going to do the other 2, which means we should have a minus 10 here and a 5 down here. Second row, here we go, minus 1, minus 8, that's minus 9, minus another 1, that is indeed minus 10, and then 3 plus 2 is 5, plus 0 is 5. So that's 5 lots of what we started with, therefore our first eigenvalue is 5. Part B, given that minus 3 is an eigenvalue of m, determine a corresponding eigenvector. Okay, so we're doing it the other way around now. We're being told that one of the eigenvalues is minus 3, therefore when we apply the matrix m onto a corresponding eigenvector, which we don't know yet, call it x, y, z, that must be minus 3 lots of that same vector. Remember, that's the definition of an eigenvector. What I can do then is put that into there, apply the matrix multiplication on the left here, and then equate the components, get 3 equations, and hopefully that will tell me some useful information to determine what x, y, and z must or can be. Multiplying this, we get 0x minus y plus 3z must equal minus 3x. Second row gives me minus x plus 4y minus z, and that must equal minus 3y. And the third row, 3x minus y plus 0z must equal minus 3z. You can see, I hope, that the first and the third are telling you the same information. The second one I can rearrange slightly. That's x plus z minus 7y must equal 0. And if I change that by multiplying by 3, 3x plus 3z minus 21y equals 0. Then I can substitute 3x in this third equation here for 21y minus 3z and get a relationship between y and z only, or not even. That gives me a 0 and a 20y, which gives me the definite fact that y must be 0. So that must be true. That's the only way 20y can equal 0. And if I put that back into the first or third equation that we got, that gives me 3z must equal minus 3x, which of course is z equals minus x. Now that doesn't give me a definitive number, but a relationship. So I can choose any number that fits that relationship. Y must equal 0, and x can be anything I like, and z can be anything so long as it equals negative x. So choose the easiest one, let x equal 1. Then for that relationship above to be true, z must equal minus 1, and our eigenvector is 1, 0, minus 1. If you have 2, 0, minus 2, or minus 1, 0, 1, all of those are fine, so long as this relationship is true between your two numbers that you've got there, and you've put y is equal to 0, then anything there is okay. That's why it is using the word a corresponding eigenvector, not the corresponding eigenvector. Hence, given that 1, 1, 1 is also an eigenvector of m, this is similar to part A, it's telling us the eigenvector, we can work out the eigenvalue very easily by applying m on 1, 1, 1, determine a diagonal matrix D and the orthogonal matrix P such that this thing is true. So first of all, I'm going to find that third eigenvalue. I'll copy the matrix there, and this is actually on 1, 1, 1. That's 0 minus 1 plus 3 is a 2, so I can see it should be a 2, but again to check I'm going to do the other 2 rows as well. Minus 1 plus 4 minus 1 is a 2, yes. 3 minus 1 plus 0 is also a 2. That's 2 lots of the original, so the third eigenvalue is a 2. Now that I've got the eigenvalues, that is going to give me an easy way to get D, the diagonal matrix, because I just need to use those 3 values. We had 5 minus 3 and 2. Put those on the leading diagonal, zeros everywhere else. That is D, and it doesn't matter which order you put those values in there, so long as what we do next is in the same order. So for p, I need to find normalized eigenvectors. So we had 1, minus 2, 1. And our second one was, oh, this one here, 1, 0, minus 1. And our third one, 1, 1, 1. To normalize these, we need to find the magnitude. 1 squared plus 2 squared plus 1 squared. That's the square root of 6. This one, 1 squared plus 1 squared, root 2. And this one, 1 squared plus 1 squared plus 1 squared, root 3. So our normalized eigenvectors, 1 over root 6, minus 2 over root 6, 1 over root 6, 1 over root 2, 0, minus 1 over root 2, 1 over root 3, 1 over root 3, 1 over root 3. And then, again, just make sure that they're in the same order. The one I'm going to use for the first column in P needs to be the one that was with the first eigenvalue 5. So that's in the order that I put them on the screen there. So P is equal to 1 over root 6 minus 2 over root 6, 1 over root 6, first column. Second column, 1 over root 2, 0, minus 1 over root 2. Third column, 1 over root 3, 1 over root 3, and 1 over root 3. If I were not in an exam, I would probably rationalize all those denominators, but in an exam setting to save time, I probably wouldn't. I'm confident you wouldn't lose any marks if you didn't. Oh, something's messed up with the PDF there. Never mind. So that's D and the orthogonal matrix P, and that is the question finished. Moving on to question 5. Use the definitions of hyperbolic functions in terms of exponentials to prove that this is true. So I'll start with the left-hand side and try and make it look like the right-hand side. 1 minus sec squared x. Turn that first of all into 1 over cosh squared x. Then on the side, remind myself that cosh x is e to the x plus e to the minus x over 2. And I always have to be careful when I square this because of that middle term. I do sometimes forget to put it in. So that's e to the x squared, so that's e to the 2x, plus 2 lots of e to the x times e to the minus x, so that's e to the 0, which becomes a 1, that's the one that I sometimes forget, plus e to the minus 2x all over 4. So if I put that in the fraction over here, that sort of gets turned upside down, as it were. E to the 2x plus 2 plus e to the minus 2x. And if I make that 1, the same thing in the denominator, so I can put them together, then it needs to be the same in the numerator as well. So that I can combine these two into one fraction. Like so. And then when you put those together, the 2 here and the minus 4 here gives me a negative 2 here. And then you can see the comparison between the two. We know from the work done up here that this thing in the denominator has come from e to the x plus e to the minus x squared. And the comparison shows that e to the x minus e to the minus x squared is the numerator. And then, of course, if you want to, you can think of these as over 2, because if it were, then those would cancel out, and that's the same thing. And that shows us how this becomes a sinh squared, over 2, over 4, and over 4. Same reasoning though, those two would cancel out. That gives us sinh squared over cosh squared, which of course equals tan squared, which is the right-hand side of the equation, proving the identity. Now we're told that in is equal to this fairly horrible looking integral. Show that in equals this, and obviously, although it doesn't use the word hence, we're going to be using this identity here. So I'll just play around with that straight away. So if we've got tanh to the power n 3x, we can write that as tanh squared 3x times tanh n minus 2 3x, and I've only done that because of the identity in part A, where we can change tanh squared into a 1 minus sech squared. So I'll do that and see where that takes me. Times by tanh n minus 2 3x. Multiply that out, seems like a sensible idea, because that gives me this term by itself, which is going to be the I n minus 2 bit here. But it also gives me this sech squared 3x times tanh n minus 2 3x. That's okay because we're going to integrate that. I can see where that's going because this is the derivative of tanh. So if I were to write this bit here, try and show you what went on in my head there for a second, like that, this term now becomes something that I know how to integrate, because sech squared is the derivative of tanh, so I can treat that as a bracket to the power of n minus 1 having been differentiated. So let's put this together. We're using the limits 0 1/3 log 2, 0 1/3 log 2 of tanh n 3x dx can now be written as 1/3 log 2 tanh n minus 2 3x. And I'll split the integral here as well. Log 2 sech squared 3x tanh 3x to the n minus 2 dx. So this first term is I n minus 2. And then I have to integrate this, but like I said, that I know has come from 1 over n minus 1 times that bracket to the n minus 1. And then the way I would do this, I tend to just get that first bit, the general form, and then think what would happen if I differentiated this. Differentiating this, the n minus 1 would come down here, cancel with that. That would become n minus 2, so this bracket would match. But then you have to multiply by the derivative of the thing in the brackets, that's where this comes in. But then you would also be multiplying by a 3 when you differentiated this. So there's actually a 3 down here as well, to take care of that 3 in the differentiation process. That's how I would think of that, but then we also need to apply the limits here. And I'm just going to pause and check that that does match, that we're on track. 3n minus 1, yes, the denominator looks good. P to the n minus 1, where p is a rational number, is the only thing left to find, and that's when we put our limits into tanh 3x to the n minus 1. Let's do that, but I don't have a hyperbolic function on my calculator, so I'm going to just quickly go through to see what these limits would be. That's e to the x, or 3x, minus e to the minus 3x over e to the 3x plus e to the minus 3x. And if x is 0, then that gives me a 1 minus 1 over 1 plus 1, which is obviously a 0. Great. But if x is equal to a third log 2, then this gives me the thirds cancel with the 3, so that's e to the log 2 minus e to the minus log 2, which can be changed into log a half. So the e and the log cancel. E to the log 2 plus e to the log minus log 2 again, bringing that as a power in takes that to log to a half. So that's 2 minus a half over 2 plus a half. 3 over 2, 5 over 2, 3 over 5. If you can do that on your calculator, great, that'll save you some time. So in minus 2 minus 1 over 3n minus 1 times by 3 over 5 minus 0. Don't know if I really needed that step. That's 3 over 5, sorry, that's to the n minus 1 still, because we can't evaluate the n, we don't know what that is. N minus 1. And that should match with p equal to 3 over 5. That's part B. Part C, apply what we've done, hence determine the exact value where n is equal to 5. That we can do. Give your answer in the form a log b plus c. So using what we've got at the top of the screen there, with n equal to 5. I5 equals I5 minus 2, that's 3, minus 3 over 5, 5 minus 1, that's 4, over 3 times 5 minus 1, so that's 12. And then we have to apply I3, so that's I1 minus 3/5 of 3 minus 1 is 2, over 3 times 2 is 6, and then we still have this term from the line above. And then I1, I just have to put that back into the original. What's that, a third log 2 of tanh 3x. So the power there is a 1, because now I've got n as 1 there. And we'll just have to do that. But I'm pretty sure that's in the formula booklet. And my calculator tells me this is 177 over 2500. Having checked the formula booklet, it is in there. That is a log cosh 3x. And then we need a third in there. And this is going from 0 to a third log 2. But again, I don't have cosh on my calculator. That's e to the 3x plus e to the minus 3x over 2. So if x is 0, that's not 0, that's going to be 1. Cosh 3x equals 1. When x is a third log 2, cosh of 3x is going to be very similar to what we had before. We're going to have the 2 plus the half, that's 5 over 2, but then it's all divided by 2. It's 5 over 4. But those aren't what comes out of this, because we actually have this log in here still, so they're going into a log. So I5 is equal to a third log 5 over 4 minus a third log of 1, and that's where it turns into a 0. Minus the 177 2500. So that should be 1/3 natural log of 5 over 4 minus 177 over 2500. Though a is a third, b is 5/4, and c is this weird 177 over 2500. There we go. That should be part C finished. Question 5 finished. They're all rational numbers. Yes, that's good. Okay, on to question number 6. The points A, B, and C have coordinates this, this, and this respectively. The plane pi1 contains the points. Determine a Cartesian equation of pi1. Okay, to get an equation of a plane, we need a point in the plane, so we can take any one of those 3. But we also need the normal. To get the normal, we can do the cross product of any 2 non-parallel lines in the plane. So if I take those 3 points, and A, B, C, if I find A, B, and AC, then I can cross those 2 and get the normal vector for the plane. So AB would be minus 1, 1, 3, minus 3, 2, 2. That gives me minus 4, minus 1, 1. That's AB, part A. Squeeze that in. And AC is position vector for point C minus the position vector for point A, minus 5, 2, 0. And then to get the normal of the plane, we cross those 2. And that will give me on the top row 0, minus 2. In the middle, minus 5, minus 0. And on the bottom, minus 8, minus 5, minus 13. Now I can use any point as my A. I'm going to use A. That seems to make sense to me. 3, 2, 2, and then the plane equation is r dot n equals a dot n. We know a and n, and r of course is just the general x, y, z. Dot that with minus 2, minus 5, minus 13 is equal to 3, 2, 2, minus 2, minus 5, minus 13. And I'm going to do both sides of this because I want it in Cartesian form. So we've got minus 2x minus 5y minus 13z. And on this side, minus 6 minus 10 minus 26 gives me minus 42. And then all those negatives don't look very nice. So just switch those around. And there we go, a Cartesian equation of plane 1. Part B, we've got a lot of information. Given that point D has coordinates this, the line L passes through D and is perpendicular to plane pi 1. The line L passes through perpendicular to pi 1 and passes through D. Plane 2 has equation that L meets pi 2 at E. So we've got another plane here, not necessarily parallel to the first, but it meets at point E, and we need to show that the distance DE is p root 22, where p is a rational number. So I'm going to approach this in stages. Working backwards, what I want to find the distance DE is to know the coordinates of D and E. I know the coordinates of D already, I don't know the coordinates of E. To know the coordinates of point E, I want to know where does the line L meet plane pi 2. Now I know pi 2, but I don't know the equation for L. So what I really want to start with is an equation for line L. We know a point on line L is D, and we know the direction vector of L because we're told it's perpendicular to pi 1, and that direction is the normal of plane pi 1, which we found in part A. So that gives me a starting point now to move forward. So for part B, what I want, I've got D, what's D? Minus 1, 1, minus 2. So the line L is minus 1, 1, minus 2, plus the direction vector, which is the normal minus 2, minus 5, 13, with a parameter, let's say t. So that's an equation for line L. Now I want to know where does that meet plane pi 2. So I'm going to put that line equation into a general point form and put it in here into this plane equation and find the parameter t that gets me minus 66. So I'll put that on the side so I don't have to keep going up and down. And r here is going to be the single point version of the line equation. Minus 1 minus 2t, 1 minus 5t, minus 2 minus 13t. That's going to go in here. So we've got minus 1 minus 2t, 1 minus 5t, minus 2 minus 13t, dot 14 minus 1 minus 17 has to equal minus 66. Minus 14 minus 28t minus 1 plus 5t plus 34 plus 221t equals minus 66. That's 198t equals minus 85. Not a very nice number. So that gives me the point at which the plane and the line intersect. I put that back into my R here, which I've got the general point for the line to find the coordinates of E. So R at that t value, minus 14 over 99, 623 over 198, and 709 over 198. Yikes, really not very nice there. So E is minus 14 over 99, 623 over 198, 709, 198. And that just came from putting this t value here back into this general point here and calculating what that would give. We also have at the top of the screen there d, minus 1, 1, minus 2. So to get the distance dE, we want the magnitude of this vector. So minus 1, 1, minus 2, minus 14 over 99, 623, 198, 709, 198, 85 over 99, minus 425 over 198, minus 1105 over 198. I hope these numbers work out because this is not looking nice. So it's the magnitude of this. So it's the square root of the square of those. That's 7225 over 198, which is indeed 85 over 66 root 22. I say is indeed because I know the root 22 was part of the question. Yes, so p root 22, where p is a rational number, that's looking pretty good. So p is 85 over 66. Okay, on to part C. The point F has coordinates 4, 3, Q, where Q is a constant. Given that ABC, F are the vertices of a tetrahedron of volume 12, determine the possible values of Q. Okay, for this we're going to be using the triple scalar product, so I'm going to take this information here down with me, that's going to be useful. This is part C, and F had the coordinates, I've forgotten already, 4, 3, Q, and we need a third vector out of this, so AF would be 4, 3, Q minus 3, 2, 2, 1, 1, Q minus 2. Now the volume, if you remember the formula, is 1 over 6 times the magnitude of A dot B cross C, where A, B and C are the vectors connecting the 4 vertices of your tetrahedron, which is why we need those 3 vectors. So I'm going from A to each of the other 3, and it doesn't matter which way around you get these because this is a cyclic situation, so I'm going to do the sensible thing and take the cross product that I've already got between 2 of the vectors and use it there, which means that this third vector is going to be this one. So we've got 1/6 of the magnitude of 1, 1, Q minus 2 dot the cross product, which was minus 2, minus 5, minus 13. And all of that from the question had to equal 12. Oh, quick note here, just saw as I went past, determine the possible values, plural, so I'm expecting 2 or more, and that is probably because of this magnitude symbol here, so that has to equal 12. So if I take the 6 over the other side, make that 72, and then do the dot product, we get minus 2, minus 5, minus 13 plus 26, and it's the magnitude of this, sorry I missed a Q, important one, minus 13Q plus 26, so that's minus 13Q plus 19, the magnitude of that must equal 72. So either minus 13Q plus 19 equals 72, or minus 13Q plus 19 equals negative 72. Because obviously when you take the magnitude of those 2 numbers, they both give you 72. Over here, that gives us minus 91, minus 13Q is a nice round 7. And over here, that's 53, and that's just negative 53 over 13. These are our 2 answers, and that is the end of question 6, I think. Just double check. Yes. On to question number 7. Okay, straight away we've been given y is equal to arc cos sec x, and we need to show that the derivative of that is sec x. Okay, a arc cos sec x. First thing I'm going to do is jump over to the formula booklet, because the derivative of arc cos is not something I carry around in my head. Here we are in the FP3 section, arc cosine on the left, second one, and here is the derivative I'm looking for. So I've got that here. This is the derivative of arc cos x, but of course we've got sec x, so we're also going to need to know what is the derivative of sec x. Back to the formula booklet. Now the derivative of sec is not here, but if you go back to P3, here it is. The derivative of sec is sec tan, and you can remember sec because it's the same except that it's negative. So it's negative sec tan, not something I carry in my head, but something that I do know how to get from what's in the formula booklet, with a little memory trick there. So bringing that across gives me these two to work with. So when we want to differentiate this thing, and we're putting sec x into this thing here, instead of x squared, it's sec squared x. Then we have to multiply by the derivative of sec x, which was sec x tan x. Now we need to make it look like sec x. So there's a lot of simplifying that should be able to go on here. First of all, we can cancel the negatives. 1 minus sec is tan squared. Sorry, 1 minus sec squared is tan squared. And we can see where this is going now. That cancels with that. And it is indeed sec x. Okay, part A shown. Then we've got a graph, a sketch, and this bit is the bit that we've shown the derivative of. So this bit is probably going to come up next. Note that x is greater than 0, and point P is a minimum turning point. So this is a turning point. Show that the x-coordinate of P is this, where Q is this, and K is an integer. Finding the turning point, we need to differentiate. We've already got part of it done, and coth, I'm going to jump back over to the formula booklet in a second. So if f of x is arc cosine sec x plus coth x, the first derivative, we've got, from what we've just done there, sec x plus something from the formula booklet. And we're still in the P3 section here, because if I put an h in here, then I put an h in here. So coth differentiates to negative cosec squared. I'll get rid of that. That's negative cosec squared x. So that's the derivative. And now we want to find the turning point, so we set that equal to 0. Sec is 1 over cosh. Cosec is 1 over sinh squared. So we've got sinh squared x minus cosh x equals 0. Sinh squared is cosh squared x minus 1. And that gives us a quadratic in cosh squared. Sorry, in cosh. Can we factorize? No, that was a waste of time. Let me quickly make this a bit easier to write, where a is equal to cosh x. So solving this quadratic would give us a equals minus b plus or minus the square root of b squared minus 4 times a times c, all divided by 2 lots of a. Oh no, I'm saying a, using a for 2 different things there, but I'm sure you know what I mean. That's 1 plus or minus root 5 over 2 equals cosh x. Now we want to know what is x, and we want it in terms of a log, so I'm going to go back to the formula booklet again. This is back in the FP3 section, and we want r cosh x is equal to this. So the way I've got it here, I'm going to have x is equal to the log of a plus root of a squared minus 1, where a of course is equal to this thing here. Therefore x is equal to the log of 1 plus or minus, I'll think that through in a second, plus root of a squared, yikes, this is horrible, minus 1. Now without going into any theory, just whacking that on my calculator with the negative symbol gives me the square root of a negative, so we know that can't be a negative, this is a positive here. Does that match what we needed? Log of q plus root q, where q is a half 1 plus root k, half 1 plus root 5, but it has q plus root q, which is suggesting that the thing inside the square root here is the same as the thing outside the square root. So let me quickly check that's true. That gives us a 1 plus a 5 plus 2 lots of root 5 all over 4. And that gives us a 6 plus 2 root 5 over 4. And then if we subtract a 1 from that, or 4 over 4, that gives us a 2 plus 2 root 5 over 4, which is 1 plus root 5 over 2. Yes. Okay, so the thing outside the square root is the same as the thing inside the square root. So x is equal to the log of 1 plus root 5 over 2 plus the root of 1 plus root 5 over 2. And that matches what we were given with q is equal to 1 plus root 5 over 2, or as I've written it there, as it was actually written in the question, and k, the integer inside the root inside of q, is a 5. Double checking that. Log of q plus root q, where q is a half 1 plus root k, and k is 5. Looks good. On to question number 8, after a little bit more work than I was really expecting at the tail end of that question. Little reminder at the top there that you've got to show all of your working on this one. Figure 2 shows a sketch of part of a curve C with equation this, part of a line with equation x equals 18, so immediately we know this is 18. The region R, shown shaded, is bounded by C and L. Show that the perimeter of R is given by this, where alpha and beta are positive constants to be determined. Okay, just note that there's a y in there, and there's a dy here. I think the formula booklet will give the formula in terms of dx, if I remember correctly. But we can start this off very easily by finding the distance here of this line, because we just need to know what are the y coordinates there, and we can do that by putting x equals 18 into here. So part A, first of all, x equals 18, y squared equals 8x becomes 144. So y is plus and minus 12. So that's 12 minus 12, so the distance here is 24 from here to here. Now rather than going from minus 12 to 12 as our limits, as I suspect here, it wants us from 0 up to 12. So we've already got beta, beta's 12. And then because we want this thing and this thing, we've got a 2 times multiplier here. So actually we've already finished, because alpha is this one here, the 24. No, let me correct myself, we haven't shown it. We have determined alpha and beta though. So alpha is equal to 24 and beta is equal to 12, but we still need to show that this is true. The perimeter is 24 plus 2 of the interval from 0 to 12 of whatever the integral formula is in the formula booklet. Here we are for arc length, the last page of the FP3 section. And here's where you needed to note that we had a dy, not a dx, in our question. So this isn't given to you, so either you can apply chain rule thinking, or you can just remember that an alternative version for the arc length is 1 plus dx by dy, instead of dy by dx, squared times dy instead of dx. So I've dropped that on the side there. So this is square root of 1 plus dx by dy squared dy. Now we've got y squared is equal to 8x, and we need to differentiate that. Implicit differentiation gives us 2y dy by dx is equal to 8. And if we rearrange that and flip this upside down, dx by dy is equal to y over 4. Therefore dx by dy squared is y squared over 16. Drop that into what we've got at the very top of the screen there, and that should give us what we need. Square root 1 plus y squared over 16 dy. Does that match now? Yes. Part B. Use the substitution y equals 4 sin u and algebraic integration to determine the exact perimeter of R. Y equals 4 sin u. Okay, I'm going to do a bit of manipulation rather than just dropping that straight in. Y squared is 16 sin squared u. So obviously y squared over 16 is equal to sin squared u. 1 plus y squared over 16 is equal to 1 plus sin squared u. Let's out my h's. And that equals cos squared u. So the square root of that, square root of this equals cos u. At the same time, we're going to need to substitute out the dy. So dy by du for cos u. So dy becomes 4 cos u du. Finally, the limits. If y equals 0, then 0 equals 4 sin u, and u is equal to 0. And that's because I've taken this from the formula booklet and putting a 0 in there gives me the log of 1, which is a 0. Then I've also got y is equal to 12. And if we put that in, we get a 3, and r sin of 3 is the log of 3 plus the root of 3 squared. 9 plus 1 is 10. Oh, not a very nice number. Now I've got everything I need just to start dropping everything in. We've got the square root of 1 plus y squared over 16 is equal to cos u. dy is equal to 4 cos u du. And the limits 0 to log 3 plus root 10. So p is now 24 plus 2 lots of the integral from 0 to log 3 plus root 10 of cos u times 4 cos u du. So if I make that 8 cos squared u du, and then I don't like cos squared, what are we going to do there? Let's just put that back into exponential form, not forgetting our middle term, as I sometimes am prone to do. E to the x plus e to the minus x over 2, square that, e to the 2x plus 2 plus e to the minus 2x over 4. E to the 2x plus 2 plus e to the minus 2x over 4. Oh no, not x. U. So that cancels with that to give us a 2. So we're going to do 2e to the 2u plus 4 plus 2e to the minus 2u du, which is much easier to integrate. we've got 24 plus e to the 2u plus 4u minus e to the minus 2u, from 0 to a log 3 plus root 10. This does not look like it's going to be nice to plug in the limits. Let's do it nice and carefully. E to the 2 log of this thing, but when you do that, we can do log of this thing squared. And I'll do the other e next. That'll be log of this thing to the minus 2 plus 4 lots of the log of 3 plus root 10. That's the first limit only. But then the second limit, e to the 0 is a 1 minus e to the 0 is gone. And then if u is 0, the 4u is also 0, so that's just 0. Like so. 24 is still there. So the e's and the logs cancel, making it slightly easier. Maybe not. Like so. I assume that's not the final format. Simplest form, it doesn't give me any clues here, but once it's simpler, squaring that gives me a 9 plus 6 root 10 plus 10 minus 1 over the same thing. 19 plus 6 root 10. 24 on the front still. Can't do much with this. 43 plus 6 root 10. And then I should try and rationalize this, I guess. 19 minus 6 root 10. Can't consider its simplest form with a third in a denominator. That's minus 19 plus 6 root 10. Oh, my calculator tells me that's a 1 in the denominator. How nice. Nearly there. That will take that back down to 24. Now there's 12 root 10s and 4 log 3 plus root 10. Quite a lot of simplifying at the end there, but I think that's the end of the paper. Part B finished. Yes. Oh, we got to the last page. I don't often use the final page of an exam, but I hope that has been helpful for you.